Question 2. Question is about sulfuric acid and its salts. Draw the displayed form of a molecule of sulfuric acid. Now you should know this from electrophilic addition across a double bond when you've done electrophilic addition. So you should know that a sulfur has got two OHs and two S to double bond O's. In aqueous solution, sulfuric acid acts as a strong acid. The H2SO4 dissociates to form HSO4- ions and H+ ions. Give an equation for that. Easy enough. Give an equation to show the HSO4 ions act as a weak acid and dissociate to form SO4- ions. So if it's acting as an acid, it produces another H+. So the HSO4- ion now produces SO4- and another H+. So it's producing H+. Both these are acting as acids. A student is required to make 250 cm³ of an aqueous solution that contains accurately measured mass of sodium hydrogen sulfate. Doesn't tell you what the mass is. I don't think that matters because you just asked about the method. So what you first of all got to do is you've got to get yourself a beaker or a conical flask and put it onto a balance and press the tare button so it zeroes it. Then you weigh your sodium hydrogen carbonate into the conical flask. That's good. That's important that you press the tare rather than take two readings, because every time you take a reading then you get increased error. So using the tare is important. Although actually if you said you took two readings before and after and subtracted, you won't lose a mark. But it's better to press the tare, and therefore you'll reduce the errors because you're only taking one reading. Then you've got to, in the conical flask, you add distilled water and dissolve it all in the conical flask. You don't transfer it into the volumetric flask until it's dissolved. It's far easier to stir and dissolve it in a conical flask rather than in a volumetric flask. It's hard to dissolve something in a volumetric flask. So you make sure it's dissolved first of all in the conical flask, then you transfer it into the volumetric flask. Important you wash the conical flask, because you want to try and wash out any remaining solution out there with distilled water and put it into the volumetric flask. Then you make up to the 250 cm³ mark and then shake it to make sure the last parts, that any last remnants of sodium hydrogen carbonate are dissolved and that it's equally mixed throughout the solution. A solution contains 6.05 grams of sodium hydrogen sulfate in 100 cm³ and has a pH of 1.72. So you've got a number of things to do first straight off here. You've got a mass in milligrams. To get milligrams up into grams, then you have to divide it by 1,000, so 0.605 grams. You can work out the MI, you can work out the number of moles of this. You've got 100 cm³, so you can work out the concentration. You've got a pH, so pH equals minus log to the base 10 of H+ concentration. If you're given a pH, you must have to work out H+. So we can do all those things first of all. So initial number of moles of hydrogen sulfate. So moles equals mass divided by MR. I've turned that into grams by dividing by 1,000, 0.605. I've worked out the MR of sodium hydrogen sulfate, 120.1. Divide the two, 5.05, 5.04 times 10 to the minus 3 are the number of moles of sodium hydrogen sulfate. Now, sodium hydrogen sulfate is going to make hydrogen sulfate ions. It tells you that, more or less. Hydrogen sulfate ions are made when you dissolve this in water, so it'll make Na+ and HSO4-. So the number of moles of HSO4- are the same, and then you can work out concentration of HSO4- or the sodium hydrogen sulfate for that matter. It's the number of moles divided by the volume in decimeter cubed, 100 cm³ up into decimeter cubed, up into a high unit value, divided by 1,000, 0.1, and it comes out as 5.04 times 10 to the minus 2. So I've got the concentration. Now I've got pH. pH 1.72. The only reason you'd be given pH is because pH equals minus log to the base 10 of H+ concentration. Reverse the signs on both sides, so minus 1.72 equals log 10 of H+ concentration, then inverse log minus 1.72, and you'll work out the H+ concentration. It should come out as 0.0191. Now I've just written a simple sort of equilibrium here. HSO4- we know from the previous question anyway, makes SO4- and H+. There's usually a link between questions. So HSO4- makes H+, so that's where the H+ are coming from. So I've written an equilibrium constant here, H+ concentration, SO4- concentration, there are the concentration on the right hand side, divided by the concentration of SO4- on the bottom. Have I got H plus concentration? Yes, 0.0191. Have I got sulfate? Well, every time a H plus is made, a sulfate's made. So 1 mole of sulfate is made at the same time as 1 mole of H plus. So the concentrations of these must be equal. So that must be 0.191. And the hard bit, I suppose, now is to work out HSO4 minus. Well, you know the number of moles of HSO4 minus at the beginning is 5.04 times 10 to the minus 3. So you know that 5.04 times 10 to the minus 3 is the number of moles at the beginning. You know the concentration is 5.04 times 10 to the minus 2. The concentration of H plus is 0.191. So if you subtract the two, because every time a H plus is made, then HSO4 is used up. So if you subtract the two, you'll work out the concentration of HSO4 minus, and therefore that equals 0.0313. So you can put that in and you can work out Ka equals 0.0117 or 1.17 times 10 to the minus 2. I've put it to three significant figures because of things like 1.72, 605 milligrams, 100 centimetre cubed are also to three significant figures. But the hard part is working out the HSO4 minus concentration by subtraction of what it was at the beginning, 5.04 times 10 to the minus 3, subtract the concentration of H plus to work out 0.313. Once you're there, then the rest of it is quite straightforward. The units, concentration multiplied by concentration, so moles divided by decimeter cubed multiplied by moles divided by decimeter cubed, divided by moles divided by decimeter cubed, another concentration. Top and bottom, the concentration on the top and the concentration on the bottom cancel, so a mole and dm3 and a dm3 cancel, so the units are mole divided by dm3, or if you take the dm3 from the bottom to the top, it comes mole dm to the minus 3. Some sodium sulfate is dissolved in a sample of the solution. So what does the sodium sulfate do? So sulfate ions. Hydrogen sulfate makes sulfate ions in H+. So if I add extra sulfate ions, by Le Chatelier's principle, it's going to try and lower the concentration of sulfate ions. So if I increase the concentration of sulfate ions here or here by adding more sulfate ions, sodium sulfate, by Le Chatelier's principle, it will try and lower the concentration of those, and it will shift the position of equilibrium to the left-hand side. In doing so, it will lower the H+ concentration. H+ concentration. H plus is acid, acids make H plus, so if I lower the H plus concentration, it's going to become more basic or more alkali, and the pH will therefore increase.